So what I want to do today is talk about continuity and what continuity means. Continuity means for a curve, for a function, and it doesn't have to be just a function. That means there's no breaks in it. There's no um, you could take a pencil and you could draw it without lifting your pencil. That's the idea of continuity. All right, you wouldn't have to pick up your pencil to draw it. All right, so how do we show something like that with mathematics? Well, it takes limits basically and the function value. All right, so this is the definition of a continuity at a point and an interior point. So we're going to have something like this. All right, some graph, something that comes, like that. All right, and this is an endpoint, and it's the left endpoint that we're going to call A, and then this would be the right endpoint B. So in this, we're talking about a point in the interior of its domain. Okay, so somewhere in here, like this, like right there, and that would be my C that I'm talking about. All right, so we know it's continuous at this value of C if three conditions are met. All right, f of C has to exist. So you would have to be able to put that in, and you have a function value at that value. Okay, and this is a continuous function, by the way, what I drew. All right, so at second thing is you got to find the limit as x approaches C of f of x that it exists. So for it to exist, we have to look at the two one-sided limits. So we've got to approach C from the left and C from the right and see if they agree. If they agree, then this limit exists. And then the final thing for it to be continuous, for no breaks to happen, is that that function value and the limit have to be the same thing. Okay? And so we're going to talk about the different aspects of this. Okay? Sorry, my phone just went off. All right. So what about if we have a function? What about the endpoint? Okay. So you can't do this because you can't do the one-sided, right? But it's this, a function y equals f of x is continuous at a left endpoint A. So that's my left endpoint A of its domain if the limit as x approaches A from the right of f of x equals f of A. Okay. So basically, we just have to show that the function value exists, that the right side, now this is weird, a left endpoint, but we have to approach it from the right side because if it's a left endpoint, there's nothing on the left. The function's on the right if it's a left endpoint, okay? So we have to approach A from the right and show that those two are the same value, okay? For the right endpoint, for it to be continuous, then we would have to look at the limit as x approaches this B value, but from the left. Why from the left? Well, we can't approach it from the right. There's no function out there because this is a right endpoint. It's the last point on the right. So there's no x values to the right that we could use, okay? So we have to approach B from the left, all right? And that's what this is saying. The limit as x approaches B from the left of f of x, and it would have to equal the function value there, okay? And if we show those things for left and right endpoints and an interior point, then we know the function is continuous. And you know what I just said, I'm not going to ask you to do the whole thing. I'm just going to ask you to do one point, okay? This is what you have to do if I give you an endpoint, okay? And then the last thing, and we're going to talk more about this tomorrow, okay? And this is a weird thing, okay? A continuous function is one that is continuous at every point of its domain. So that's the definition, okay, of what a continuous function is. A continuous function is one that's continuous at every point of its domain. So if it's discontinuous, but that point is not part of the domain, then it's still a continuous function. That's weird. We'll talk about that tomorrow though, okay? All right, let's go to the first problem that we're going to look at. So the next thing we're going to talk about is the different types of discontinuities. So it's not going to be continuous. So there's a break. This hole right here is actually a break in the graph. So there's a discontinuity there. And this one, I'm going to tell you right now, holes like this are always called removable discontinuities. All right. So f of x is this function x squared minus 9 over x minus 3. That's a difference of squares. Okay, so this becomes x minus 3, or we could rewrite it like this, x minus 3 times x plus 3 over x minus 3. My x minus 3's cancel, and I'd be left with x plus 3. All right. Now, I should say this. These are not really equal to each other because this one has a hole from last year. This one has a hole, but then this one doesn't. Okay. And that's kind of why this is called a removable discontinuity, because this one is this entire line. All right. And so we can replace this function with this and be gosh darn close, except for at that one point. Okay. So the very first thing is, does f of 3 exist? So f of 3, if we put it in here, okay, it makes the numerator 0 and the denominator 0. So that's 0 over 0. So that means f of 3 does not exist. All right, the second thing we need to do is look at the limit. What is the limit as x approaches 3 for f of x? What does that equal? Or does it not exist? So to do this, we got to look at the limit as x approaches 3 from the left of f of x. And we have to look at the limit as x approaches 3 from the right of f of x. All right, and if we can read it off the graph, if we approach 3 from the left, okay, so right here's 3. If we're on the graph, if we approach 3 from the left, it's going to get closer and closer to the open dot right there, which is 6. And if we come from the right, it would also be 6. Okay, those are in agreement, right? So this is equal to 6. All right, so the third thing is, are these two the same? Is the limit and the function value the same? And so we would write the limit as x approaches 3 of f of x does not equal f of 3. So all of these this has to exist, the limit has to exist, and these two things have to equal, and that's not the case, right? All right, so here's how we know it's a hole. It's when the limit exists. So when we will always have removable discontinuities, all right, when the limit exists, but either this one fails or this one fails. Okay, so let's write this, okay? If the limit exists, I really wish you guys were writing this too, along with me. The discontinuity is a removable discontinuity. All right? And so that's why it's called a removable discontinuity, because the limit exists, but it's not continuous still. If the limit exists and it's not continuous, it has to be a removable discontinuity. Let's go to the next problem. All right, so for this next one, all right, the discontinuity happens right here, okay? And that's where the break in the graph happens right here. Here we have an open dot and here we have a closed dot. One thing to notice right here is this is a difference of squares, all right? So we could write, I'm gonna write this, x squared minus 4 over x minus 2 could be broken down into x minus 2 times x plus 2 all over x minus 2. And then simplified, that becomes x plus 2. And the simplified version we can use to help us find limits if we need to. Okay? We can also do it graphically, all right? So we want to go through these three statements. The first statement is, what is f of 2? So f of 2, well, it's not this open dot, it's actually this closed dot, right? F of 2 is actually equal to 1. So it exists. It's just 1, okay? The second thing we need to go through is to find the limit as x approaches 2 of f of x. So we can use this, okay? We can't use this, okay, but we can use this to determine the one-sided limits. So we need to find the limit as x approaches 2 from the left of f of x. and the limit as x approaches 2 from the right of f of x. Now, graphically, as we approach 2 from the left, that'd be coming this way, right? We'd be approaching this open dot, which is 4. And we'd be approaching from the right, we'd also be approaching this open dot, which is equal to 4. Now, we can, with this one, is plug the 2 in right here. So that'd be this 2 right here. We could do a direct substitution. We can't do it in this one because it makes 0 over 0, but we can plug it in here and it'd be 2 plus 2, which is 4. And that's another way you can get these 4s, okay? So these are in agreement. So this is equal to 4. And then, all right, so here's the problem. The limit and the function value they're not the same thing. And so that's where our problem is, okay? So the limit as x approaches 2 of f of x does not equal f of 2. And once again, the limit exists, right? And because the limit exists, that means we have a removable discontinuity. So there's just a little itty bitty hiccup right here, not a big, huge one, okay? So we would say, okay, f of x has a removable discontinuity at x equals 2. And I should have said that on the last one, okay? So I'm going to state, okay, what type of discontinuity it has and at what x value. All right, so let's do the next one. Actually, let's go back. So on this, we would say, okay, because I forgot to write it, all right, that there's a removable discontinuity at x equals 3. So f of x has a removable discontinuity at x equals 3. So for this next one, these are going to be non-removable discontinuities. All right. So here's this function. All right. And this could also be written as a piecewise function. So this is going to happen. This is going to be called a jump discontinuity because the function jumps from right here to right here. And then we'll talk about why it's called a jump discontinuity in just a minute. Okay. So to right here, the break in the graph happens at x equals 2 again. So we got to go through, okay, so what is f of 2? So f of 2, and this is an open dot, this is an open dot, there's nothing, right? There's no value here. So f of 2 does not exist. Okay, so the next thing we need to do, okay, what's the limit as x approaches 2 for our function f of x? So we have to do the one-sided limits. The limit as x approaches 2 from the left of f of x, and the limit as x approaches 2 from the right of f of x. And from this one, we're going to do it graphically, okay? So from the left of 2, as we approach it, okay, we think it's approaching negative 2. So to the left, as x approaches 2 from the left, f of x is approaching negative 2. And from the right, as x approaches 2, the function is approaching positive 2. And those aren't in agreement, right? Those aren't the same. So that means the limit as x approaches 2 of f of x does not exist. And then if this doesn't exist and the function doesn't exist, well, heck, they can't equal each other. Okay, so the third thing is the limit as x approaches 2 of f of x does not equal f of 2, okay? And the reason it's called a jump discontinuity, whenever, all right, the one-sided limits are different, that's always going to be a jump discontinuity. That's always going to be called a jump discontinuity because just to the left of one is one value and just to the right is the other. And there's all of a sudden this jump in X value. So up here, this one previously is not a jump discontinuity. Okay. I'll slide it back up in just a second. Okay. So what we would say is f of X has a jump discontinuity at X equals 2. Okay, so I'm going to slide it up. Okay, so you see the difference is like as you approach 2 from either side, you're approaching 2 different values, right? That's what's causing the jump discontinuity. Whereas this one above, sorry if that makes you dizzy, all right? As we approach 2, they're not different, right? So there's not this jump. I know the function value's down here, but that's not a jump, okay? The 2 one-sided limits aren't approaching different values, so there's not this huge jump between values, okay? All right, so that's why this one is not a jump discontinuity. So I want to say this, in the past few years, a lot of people are thinking this is a jump discontinuity. It's a removable discontinuity because the limits from either side are in agreement, okay? Whereas this one, slide it back up. I'll try to go slow so I don't get you dizzy. It's like, Mr. Mitchell, you're making me sick. Okay, that's not funny, guys. All right, so this is coming in from both sides. That's why it's a jump discontinuity. All right. Okay, let's go to the next one. Okay, so this next one is called an infinite discontinuity. Okay, so this, let's just go through it. Okay, so it's happening at 4. All right, and this is supposed to be a dashed line, but it kind of got printed as a solid one. All right, so at 4, right? So we got to go through, and what is f of 4? Well, f of 4 doesn't exist. Okay, so now we need to find the limit as x approaches 4. So the limit as x approaches 4 of f of x. Okay, so that means we got to do the limit as x approaches 4 from the left of f of x, and the limit as x approaches 4 from the right of f of x. So as we approach 4 from the left, then our graph is going down, right? So that would be negative infinity, okay? And as we approach 4 from the right, it's going up straight up, right? So that's going to be positive infinity, all right? And because these aren't number values, all right, then that means that this limit does not exist. All right, so, and if neither one of them exists, they can't equal each other, right? So the third statement would be the limit as x approaches 4 of f of x does not equal f of 4. And this is why it's called an infinite discontinuity, okay? When the one-sided limits are some type of infinity, then that's what's telling us it's an infinite discontinuity, okay? So this just has to be some type of infinity. So one could be positive infinity, one could be negative infinity. They both could be positive infinity. They both could be negative infinity, or even just one of them is infinity. Okay, like the natural logarithm. The natural logarithm, in fact, all logarithms have an infinite discontinuity. Okay, all right. So every time you have a vertical asymptote, you have an infinite discontinuity. Maybe that's a better way of saying it. Okay. All right. So f of x has an infinite discontinuity at x equals 4. All right. And how do we know it's an infinite discontinuity? Because the one side limits, one or both, are equal to some type of infinity. All right. Next problem. All right. So this one I'm going to tell you is the hardest one to understand. I'm going to say this right now. I will not test you on this one. Okay. I will not test you on what's called an oscillating discontinuity. This is just FYI. Okay. If you go into higher math, that's when you're going to deal with this more. Okay. So don't worry about this. This is just out of curiosity. Okay. I just want you to know there is another discontinuity, and it's called an oscillating one. Okay, so it's called oscillating because as you approach a value, that's why this is all like crazy in here, and you can't even see the graph because it's just jumping all over the place, kind of like a Richter scale, like we had an earthquake or something. Okay, so it's kind of like that. All right, so this is happening at x equals 0. Okay, so it's even hard to see. That's why I don't want to test you on this. I mean, it's even hard to see. Like you can't tell like where it's happening at, but it's in this case it's 0. Okay. So we go through this process. Okay, what's f of 0? Okay, so f of 0 would be sine of 1 over 0, but 1 over 0 is going to cause a vertical asymptote, right? Yeah. So it's, and then you're putting this, well, I should say this, it's going to cause this to be a really big number, okay? All right, that you're putting into sine. And so it's just bouncing around like crazy, okay? So f of 0 does not exist because you'd have 1 over 0 here, okay? And then the second thing is this, okay? The limit as x approaches 0 of f of x. And so we'd have to do the limit as x approaches 0 from the left of f of x. And it's just bouncing around, okay? So that means it does not exist. And the limit as x approaches 0 from the right of f of x. Okay, so from the right, it's bouncing around, so it still does not exist. And those don't exist, so this one can't exist. So it's like, that's when you have an oscillating discontinuity. Well, I shouldn't say that because you probably could have this for other reasons other than oscillating discontinuity, but this, like nothing works, okay? All right, and the third thing would be the limit as x approaches 0 of f of x does not equal f of 0, okay? And this is called just an oscillating discontinuity, all right? So f of x has an oscillating discontinuity at x equals 0. All right, so that's all the types of discontinuities there are, okay? And so for the first test, okay, you're gonna have to be able to identify, here's a discontinuity, what type is it and why, okay? And going through these three statements is the why, okay? All right, you can also look at it and go, oh, that's an oscillating, oh, that's an infinite discontinuity. I mean, if you have a vertical asymptote, you know that's gonna be an infinite discontinuity, okay? If you have a hole, you know that that's going to be a removable discontinuity, okay? All right, let's go to one problem I want to do with you. So for this, okay, I'm asking you to find each point of discontinuity. One thing we need to point out is what's the domain? Okay, so the domain, this function starts at -1 and includes -1, so we're going to use a bracket, comma. All right, and then it's going to go all the way to here and then back up. Now, this is an open dot, but that x value is being included because here's a closed dot. All right, and so we're going across, and here's an open dot, but that x value is being included because it's up here. And then we're back down here. And so the domain would be -1 all the way to 3. So it's included all of these x values, okay? So where are there breaks in this graph, okay? So there's a discontinuity at this x value and also at this x value, okay? So we have discontinuity at x equals 1 and at x is equal to 2. Okay, so which of the discontinuities are removable, not removable? Give reasons for our answer, okay? So this one right here at x equals 1, so we're going to do a formal write-up here, but this one would not be a removable one. Why wouldn't it be removable? Because as we approach 1 from the left, it's approaching this open dot, but from the right, it's approaching this closed dot, all right? And those are two different values. That's actually a jump discontinuity, okay? So the limit, remember, a removable discontinuity, the limit has to exist. So as you approach this value right here, x approaches 2 from the left, you're approaching this value. As you approach it from the right, you're still approaching this hole right here, which is at 1, right? So this one's the removable discontinuity, okay? All right, so here we go, all right? So f of 1 is equal to 1. The limit as x approaches 1 of f of x. So to figure that one out, we got to do the limit as x approaches 1 from the left of f of x. And we also have to do the limit as x approaches 1 from the right of f of x. And from the left, it's approaching this value of 2. And from the right, it's approaching the value of 1. And so those are in agreement. So this means the limit does not exist. And because that doesn't exist and the function value does, the limit as x approaches 1 of f of x does not equal f of 1. And we have a jump discontinuity at x equals 1. Slide it up a little bit. All right, how about the next one at 2? So let's find f of 2. F of 2 would equal 2, right? Because it's that closed dot right there. That's the function value right there. What's the limit as x approaches 2 of f of x? I should have said this function is called f of x, all right? So, because I'm using it all over here, right? All right, so then the limit as x approaches 2 from the left of f of x, the limit as x approaches 2 from the right of f of x. Okay, so as we approach 2 from the left, the value is 1. As you approach 2 from the right, the value is 1. Those are in agreement, so that means this limit is equal to 1. But the function value and the limit, they both exist, but they're not the same, right? And so that is what's causing us, I shouldn't say that. It's that the limit exists is why we have a removable discontinuity. It's that these aren't the same, that we have a discontinuity in general, okay? So we take the limit as x approaches 2 of f of x, and we say it does not equal f of 2. They're not the same value, okay? If they were, then we would say it's continuous. We wouldn't be saying there's a discontinuity there. And so this one, because the limit exists, we would say that one's a removable discontinuity at x equals 2. And that's what we would say. All right, guys, and that's it for today. I'm trying to work on my saying okays. How many times did I say okay? Like, I bet it's like 600,000 times. All right, I'm trying to stop. All right, intervention. All right, I'll see you guys later. Take care.